All right, here we go. Tesla coil log entry number 4. Here is the setup. We've got a few different things, enhancements, maybe, we'll find out. First thing you could probably notice is that the Tesla coil, the resonator tube, is a little bit bigger. You can see it in the background, there's the old small one. And the dimensions of this is actually specific. What I did was I took some measurements that the Earth has, and what I decided to try out and do was I took the circumference of the Earth at the 60-degree latitude line and took that circumference and actually scaled it down to with the golden ratio constant. And what it ended up being is roughly the 37th magnitude. So dividing that, the Earth's circumference at the 60-degree latitude line, divided that down by the golden ratio to the 37th power. And it came out with this circumference. Then what I did was, to get the length, is that basically I cut out a cylinder. It's basically like taking a cylinder, creating a cylinder within the Earth. So what I did was this cylinder matches the 37th magnitude scaled down with the golden ratio number from the cylinder that the Earth makes between the two north and south 60-degree latitude lines. So the distance between those two lines is the 37th magnitude scaled down. So the distance between the 60-degree latitude line north and to the 60-degree latitude line south. So that distance on the Earth, divide that down by the 37th power of the golden ratio constant. And then I get this Tesla coil. So this Tesla coil matches a cylinder scaled up to the 37th power of the golden ratio constant of Earth. Trying it out, we'll see what happens. And when I calculated the rough estimate of this resonance, the resonance that this should have, and it's depending on what you do. Well, I played around with two different things. I took 7.83 and I doubled that, right? I just double it, just all the way up to, in megahertz, just so you could see all those numbers are. And one of the numbers is what actually comes up close to the powers of 2. If you take 8 to the powers of 2, or whatever, computer logic, your powers of 2, for bits and how all that works. It's pretty close. So like one of the numbers from 7.83 is close to 512 kilohertz. And then, or if you take 7.83, multiply it by the golden ratio and just keep doing that, the other close number is like 502 kilohertz. And this should resonate at roughly 508 kilohertz. So it's basically dead middle between both of the two numbers. So we'll find out what happens. If that's actually special or not, or if it doesn't even matter. But that's just what I decided to do to make this guy. And the wire size is 32 gauge. So it's like 1,200 turns, give or take, I believe. I just took the distance, divided it by the diameter of this wire, and that's how I didn't count the turns out, but calculated it out. The other thing is we have a brass rod now. So going all the way down the center, and I just covered up the top with electrical tape. So this just slides right through it, goes all the way down. You can see it in there. I put a little tape down there too to try and hopefully stick it in the middle. And make sure we have that slotted right. Get it to focus. All right, that's roughly not centered. All right, I think we're good there. Try and get it centered as much as possible. Okay. You can make, oh, I want this to turn. So you can see the secondary right there is just sliding out the bottom. So that's the bottom of the secondary. The top of the secondary goes out right there. And then we have, hopefully this is all still connected. Get it to focus properly. So the yellow wire goes to ground. The green one flows into our transistor Slayer exciter circuit. I believe it's this guy. So it's gonna join a junction at the base. This going into the base of our transistor. Sorry, get it to focus. So that's the base, and then the collector, and then the emitter. So what I've actually done, so they're both PNP transistors, and they are kind of wired in parallel. So we just, for the second one, we just have the collectors joined and the emitter joined. You can see the base is empty, blank. That's because when I had it here on the breadboard, that's how I originally had it, but I had the base just off in La La Land, not connected at all. And it did run differently, actually, when I had the base connected within the parallel versus when I just took it out, then it worked. And I think it actually ran better, more efficiently than when I left the whole second one disconnected altogether. Like, as in, what I mean by is not having the collector joined and the emitter joined. So we'll see if I can observe that again, because that was something that happens, but I didn't really log it, and I didn't really think too much about it. So we're actually going to dive into that now, if it actually was running more efficiently, or not, or maybe it didn't matter. The other thing is I'm researching is I'm trying to use this system to self-cool the thing that is resonating it. So there's a couple things. There's the Peltier effect, with the three things. There's the Peltier effect. There's cooling via rapid collapse and expansion of a magnetic field. And then there's also, maybe back to two things. I don't know what the third thing was. I just lost it. Okay, so with the Peltier effect, we've got, and maybe I'm butchering that name, but whatever. So this is actually also kind of reminiscent of when you'd have when you build your own capacitor. You've got the alternating rails here sliding into each other. Right now, obviously, they're touching, but you would essentially have your hot plate here, the teeth, and then you have your cold plate. Now, what I'm doing is going to try to have, I don't know, testing this out. So I'm having this rod slide through it to see if it'll help with inducing anything. Oh, the third thing, thermal acoustic cooling. So another thing is, coincidentally, part of thermal acoustic cooling, it has to do with a resonator tube. Well, what is a Tesla coil? Tesla coil is a resonator tube. So theoretically, we have all of the components to somehow do the self-cooling and utilize the heat that comes off of this transistor to power the system. whether we could actually use that as energy back into the system, or to just try and simply dissipate that heat and keep the transistor cooler. That's all that I'm really looking for right now. We're just gonna play with it, but I keep thinking about it, like we should have all the components necessary to somehow create a cooling effect with the Slayer exciter Tesla coil circuit that we have and the rod down the center. And we just got to play with different configurations with how we build the dang thing, right? We're learning that geometry is key as, you know, part of our building, and not necessarily just the circuitry. And the geometry is a core part of how things work. And so, yeah, we'll just play with this and see how it works. What we're also going to do right now so for the Slayer exciter circuit, get back to that, we're going to use the Rodin coil as our primary for now, just to see what happens. Might be too many turns, but we'll see. I'll show you. So we got the pot, the 100K pot. It's probably too much, too sensitive, but it's what I'm going to just use right now. I'm not going to switch it out. That is going to the base, and then we have power, the positive power, since this is the PNP, so positive power is going to our emitter. And then, so it's not connected right now, but I'll show positive, so it's the power supply, it's not on. Positive, and then we'll have our negative. I'll be connecting the negative to here. So the negative will go into the resistor, which will then flow into the base, and that's our circuit. The collector flows to our Rodin coil, and then the output of the Rodin coil goes to the negative. So do that again. So we have one lead of our Rodin coil going up to the collector. You can see I'm wiggling that right there. And then it's gonna exit out the Rodin coil. Well, because PNP, it's gonna flow this way. So we'll join the negative there, goes into the pot goes to the base, but the negative will also split and go into the Rodin coil, which will then hit the collector and out the emitter. But it's negative, so it's probably flowing the other way. And then we have the rod is just going to a jar, and then our secondary is also grounded to that jar of sand. And again, this is just a brass rod, which is an alloy of copper and zinc. This part is not connected, but I'll show you. I've showed it before, but this is just an aluminum disc cut out. It's just, all it's doing is sitting on top of another Rodin coil. So the difference between these two Rodin coils is that this is a 9-strand ribbon. So there's 9 strands in this ribbon for the wire. And this one wraps all the way around this way, and then wraps around to come around this way. So it's just one coil with one junction to wire up. Or not one coil, but one full wire that goes both directions. This one is 24 strands to the ribbon, but it's also 2 separate wires. So so one wire wraps one way. So it's the same winding, but rather than just the one junction, because it's 2 separate wires, you're gonna have 2 junctions. So gotta wire these in series, and the other side that in series because you have two cuts rather than just the two ends. You have 4 ends. And then this is 3 windings each, so there's 6 layers in total if you count both wires, but each ribbon strand wraps around 3 times. So 3 this way, 3 this way. So that's what's special about that one. But we're not using it. As you can see, it's cut, disconnected. I had a lot left over and I was using it like that, but there was a lot of loops on the ground, so it basically made a bunch of more tiny little coils on the ground when it's just laying on the floor. So I ended up just cutting it, and yeah, I just haven't put it back together. But otherwise, there is just the one gator clamp into this plate because it still might get some induced current, which maybe we'll go put it up on, you know, induce current into this plate. Anyways, no matter where it's getting it from, it will go hopefully into this breadboard, but I'm not necessarily looking for it. It's just connected to a wow factor that how the heck is it working. And I've showed this before, but all it is it's a capacitive voltage divider. So instead of a resistor, it's capacitors. Instead of 2 resistors, it's 2 capacitors, and these are electrolytic, or they have a polarity to them. So this side is positive, and then this is negative, you know, negative facing. You can see the negative lead, and then the negative lead is on this side. There, you can see that. Okay. So then it's a full bridge rectifier with the diodes. So you can see that the negative here splits off. That forms the negative junction. This goes into the positive junction over here. So you can see then this positive side splits off, one into the negative, one to the positive side. That forms our capacitor bank, and then we have another full bridge rectifier where we will leverage the power. But right now, I'm not really doing anything with it. I do just have a little tiny fan connected to it, so if something happens and that's running, cool. So I think that's everything. We, again, just have a compass just for detection, and a ferrite magnet, again, to maybe get a tone out of it. Another detector device, essentially. And yeah, I think I've explained everything. Testing out cooling with this. Hopefully it's not too much interference up here. I'm just starting it out up here, see what happens. But like I think I mentioned before, maybe it's that this needs to go inside and down at the bottom and inside the resonator tube, so the heat gets pushed through. But I kind of want it to get induced into this rod, and that's kind of why I've got it through the center. But you know, I might have to play around with this more. Maybe I have to make, you know, wind a coil in here on each side or something like that, or just one coil threaded through and then slot this on that side. I don't know. We'll play with it, but all right, with that said, I think I am gonna put the phone on the stand and fire it up. Okay, so fire this up. And with this setup, you do not want to start with 30 volts. We'll just start at 12 volts. All right, 12.5. Okay. I'm going to connect the negative in Okay, we're connected. Not reading anything. So the ends, I didn't show this in the other video, in the first part, but this is the end of the secondary right here. Oh, you can kind of see it on the camera. Right there. Obviously the other end that we're gonna go in is up this way, so it's right here. Yeah, I don't think anything happens. It's happening with 12 volts. Pretty sure I've got everything wired right. I'll just crank it up. All right, do not put the resistance down. Oh. Yep. Some fun stuff happens when you actually turn the resistor down to 0. The pot all the way down. All right, here we go. So it seems like I had fried one of my jumper cables, so that's why stuff wasn't working. A couple hours later, after troubleshooting my transistors and both NPN and PNP and power supplies, and yeah. All right, so we're gonna get it going. We're at 18 volts. I don't know how I'm gonna cut up the videos with the big failure there. I don't want a long video of you guys just watching me dick around and troubleshoot doing nothing. So I've got this coil. I think I showed it, but I'll show it again. It's just what you could get at Menards or Home Depot or whatever your hardware store is. That's what the box is. This is just a copper piping. It is 1/4. Let's see, without reflection. 1/4 diameter. And so instead of the rodent coil, I just think we'll try it again. I just think the rodent coil is going to be too many turns for a primary. Right now, I've just got it connected at the bottom, spinning clockwise, which is the direction that my secondary coil is wound. So, and I'm only going up to, let's see, 1, 2, 3 wraps around. So I'm not all the way to the top. I'm at 18.4 volts. Let's just start with 20 volts. Okay. Connecting in the negative. And nothing. Okay, we got it back working again. I'm sure the rodent coil is just not going to work because it's got too many turns. Just how a transformer works. So we're connected into the copper piping. We're going to go about 3 turns. We're at 20 volts because I'm assuming since this thing has way more turns, maybe roughly 600 to 800 more turns than the tiny coil of wire for the secondary. It's going to be more powerful. So let's connect it and see what happens. Okay, 60 millivolts, or milliamps, sorry. Ooh, there it is. Okay, well that's pretty weak. I mean, granted that it's just set on top of the rodent coil, and the rodent coil turns to be You know, it's fairly high up, so this coil could probably get lowered. But what's our warmth? We just dislodged. Did we get sparking? Okay, no sparking. What's interesting is I swore I thought I felt it get colder. As I raised it. I'm just gonna put on a glove. Left hand here. Okay. So I can keep it pressed down. Now, I wish, let's see. What did we lose? Oh, we lost. Okay, what did we do? All right, what popped loose here? Something came loose. Just a matter what. Oh. Okay, we're back. Guess that was on the teeth very well. They're actually really not that much stronger. Well, let's crank her up, see what happens. 23 volts, 24 volts. What if interesting. Okay, it really doesn't like one turn. Doesn't like 2 turns. But it likes 3 turns, 4 turns, 5 turns. Let's just use the whole pipe. If that's the case, yeah. Oh yeah, way better. I'm hearing sounds. Oh, 300 million. Jesus, we just jumped. Okay, I better check on that. Wait, are we just breaking out? All right, I disconnected the negative. I'm hearing sounds. I don't know if it's just breakout, but. Oh yeah, we ain't even warm. Damn, all right. Oh yeah, we're breaking out. Okay, nice. Okay, so I just haven't had a Tesla coil that has done that for me yet, so I'm not used to it, of it just breaking out. Oh yeah, there it is. I keep that here, and there's the hiss. Okay, I'm gonna do a couple more things before I wrap up this log. I thought I may have noticed this get colder when I slid this up. So I've got it held up with some electrical tape. We're just gonna see what happens. And the new addition too is I have this white cable, and that's going to that breadboard circuit with the 2 full bridge rectifiers over here. We're gonna see if we have this green cable going to ground and the white cable down here. I'll plug it, unplug it. Let's just get her fired up. Nice thing is that I'm only running about 25 volts to get that to break out. So just gonna put this up. Okay. Now, obviously, all right, that's breaking out pretty good at 24.8 volts, 480 milliamps. So we're gonna make it so it doesn't break out. So now we're using up that extra power instead of just excess. And went all the way down to 130 milliamps. I think, is that the ozone smell I'm smelling? Okay, we'll keep this. What's this? I can't get the jar to resonate yet, but I'll do this with my other hand. I just want to see if I can feel heat. I need to get like a mechanical temperature gauge. I'm not getting any power over here. What if I disconnect ground? Okay. I do feel some warmth. Oh, should crank up the voltage. But I suppose we do have, well, I don't know if that's affecting if we got ground there, but then a wire going over to a circuit over here. All right, let's go to 30 volts. Trying to get it to exactly right, 30.2, 30.1. Come on, Oh, 29.9. 30, all right. Oh, we do have like a sweet spot, like right there. And then it goes away. It's like when there's breakout, it actually gets brighter. See that? There's like a sweet spot for where it's completely out, and then you take it away, it's coming on, but it makes a sound when you're too far. It goes out when you're on the other side, like too close. But there's a sweet spot where it breaks out but makes no noise. And that seems to be where it's brightest. Where the breakout is the strongest but makes no noise. It's like just clean. Oh, the wire's getting too crazy. There we go. Right there. Gotta stop breathing. It's too shaky. No wonder how good that's coming on the camera. It's about right there. We do oscillate between 500 milliamps to 190 milliamps, depending on where the light is. When it breaks out, it jumps up to 540 milliamps. All right, let's check temp. Yeah, we're getting warm. Whoops. Keep that there so we don't break out. It's interesting. I wonder if the heat needs to be on the bottom of this resonant tube. The problem is, well, you know, I could probably do some drilling. Drill the bottom of this, my 3D printed threaded tube here. It's just a flat bottom, so maybe I could drill the bottom and run the wires, but in order to get this whole thing in, yeah, I gotta run all the wires somehow. It's definitely more powerful. But this is not being refrigerated. So we got more work to do. More tests, more experiments, looking at thermal acoustic cooling, the Peltier effect, and temperature differentials from rapid magnetic field oscillations. So those are kind of the three things that I think we have in our system. We should be able to tap into one of those three phenomenons, I guess is maybe the best thing to call them. But, yeah, alright, I think that's going to be it for this. I just wanted to do an up-close look at the two heat sinks that I have taped together here. This is what holds my two PNP transistor circuit for the Slayer exciter circuit. If you kind of just look at it, sorry, get it focused. It's kind of reminiscent of what a aluminum capacitor would look like with the teeth going in between each other and the alternating pattern. So it's kind of cool. So I don't know if maybe we could, if putting a coil threading through those teeth. So we have this rod here going on this side. So we technically have, if you think of like the Peltier effect and how that looks, how those thermoelectric devices are. This is kind of like the hot end of the heat exchange. And then this is sort of the cold surface. So we have like the cold energy coming out from the rod and down the center. And then we have capacitance in between. And then if we thread a coil, maybe make a loop from starting here, wrap around, out, come up here, come out this side, and coil. But maybe not on this one. Maybe do that on here. And then it can catch, it can kind of get an induced current and maybe create a magnetic field that oscillates, whoops, and cools this. So maybe that's the next step we'll try before we venture of trying to get that circuit housed inside here, down in the depths. So that's all.